Hello viewers, welcome back to Dexter's Tech Lab. It's been quite a while since I made a video. I do apologise. There has been a whole lot going on and Christmas happened and I have to work through Christmas and we had relatives coming round and I was waiting on things for the Dylan that we're going to talk about in a moment. So my humble apologies to everyone about not making videos for quite some time, but this is here to rectify that. So to start off, I have a couple of really big thank yous to get out there. The first one is somebody who was instrumental in helping to get these two machines working, and that is Jez of Peak Electronics. You may or may not have heard of Peak Electronics, but they have been manufacturing their own range of test equipment here in the UK, not far from here, over in Buxton. They have a fantastic range of little useful bits of test equipment and they're absolutely awesome. They are completely and utterly a small business and what they do with the team that they have is absolutely amazing. If you want to go and check out any of their products, there's going to be a link in the video description, so you can go and check out Peak Electronics and have a look at some of their test equipment. As you can see, some of it showing up here. Highly recommended. Right, let's get to the meat and potatoes of this video. We are talking about the Quantel HAL and the Quantel Dylan video compositing system that I've been making a series of videos on. So you've seen previously, I hope, the previous episodes where I have managed to restore the HAL, the actual main computer part of it. That has now been fixed and as far as I can tell there's nothing wrong with it, touch wood. So in the last episode I was looking at the Dylan disk array. So the Dylan disk array provides the video storage that the HAL uses when you're doing video compositing. So in the last episode I explained roughly how this machine works. I also explained how the power supply had failed and that was off being repaired. That has been done, so that is now fully working, tested and everything, and I can literally turn this on now and I have no fear of it bursting into flames. So that has been done. So once I had now a working power supply, I could then turn the machine on and actually try to start to use it with the HAL. Now there is a fair bit of detail to go into on here because I actually don't want to skimp over it. I actually want to talk about it because it kind of explains a little bit about how this machine works. I've spent several weeks on this now and I've learned a lot about it, and the whole architecture and the way the system works is absolutely incredible when you've got to think back to when this was actually available to buy. You know, this dates, I think these came out in 1993, and as I explain about what they're capable of doing, you'll probably start to realise that these were quite a special bit of kit. This episode of Dexter's Tech Lab has been sponsored by PCBWay, your one-stop solution for PCB prototyping, PCB assembly, and this is not just normal PCBs. You can do flex rigid, all this sort of stuff. They also offer 3D printing, CNC machining and milling, sheet metal fabrication and injection moulding. So tons and tons of options there for turning your current project into reality. These two PCBs, well, I actually had a pack of 5 of these made. These were made by PCBWay for a little project that's coming up in a future video. So this just does prove that I do have PCBs manufactured by them. This isn't one of my own designs. This was literally picked off the internet, the files sent to PCBWay, and then a week later or so the boards turned up and they're absolutely perfect. So that just goes to show how good they are. Right, here we are. So as I said, I wanted to explain a little bit more about what has actually happened with this machine. Obviously, because I've been trying to diagnose it and get it working, because I have to let you know it's not working yet. that I've learnt a huge amount about it, down to some quite technical things, and it's fascinating learning about it, to be honest, and I want to try and explain some of it to you guys. So let's explain what actually happened when I turned this on for the first time. So the power supply was all fixed, so it didn't go bang, it powered on. Absolutely fine. I can actually do that now, and it turns on. Now when you turn on this machine, all that happens is you power up the electronics, and the drives do get power, but they are all configured so they don't spin up until they're requested to by the host. So all the drives are all powered up, but they don't do anything until the machine says, okay, can you please spin up your disks. So it just lies in this inert state, doing nothing. There is zero software on this machine right at this point. And indeed, if you start to scope around with an oscilloscope, you can see clocks and things like that, but there's literally no activity on anything else. So yes, it is completely blank in terms of software and all that sort of stuff. Now I'm going to explain how the boot process actually works and how the software is loaded onto this machine. There is one CPU running the whole show, and that's this one over here. This is actually an InMOS T425 transputer. The transputer was a family of processors developed by InMOS. They were really quite innovative CPUs at the time. They were designed to be interlinked, so you could actually have a multi-processor array of the transputers, and they had a number of mechanisms built into them to aid multi-processor functionality. So it's using a transputer as the main CPU. The transputer has 4 megabytes of RAM associated to it. Now, as I said, there's no software in this when you turn it on. So how does the software get onto the machine? Well, it comes over the data cable, which interconnects the Dylan to HAL. That is made up of 2 parts. There is the part that transfers all of the video data, and then there's the other part, which is the link. The link uses InMOS's own transputer link, which is a differential serial connection. So you have 2 wires going from Dylan to HAL and 2 wires that go from HAL to Dylan. These links are serial, and they operate at about 10, well, not about, they operate at 10 megabits per second. So quite a reasonably fast link. The transputer has a quite an unusual feature which allows it to boot over that serial link. So the way it works is the Dylan is powered on and the processor is in a non-running state. HAL will then transmit the raw code, the actual raw software, over that serial link, and the transputer will then clock that data into the RAM. And once that's completed, the CPU is reset, and then it will begin execution of the code that was delivered over the serial link. And then you can start bringing the system up to a level where you can actually have proper two-way communications. And that's when Quantel software takes over. There's actually a set protocol, a set way to actually transmit the data, and as the packets of data come in, they're transferred into RAM, and then the CPU acknowledges little packets back to HAL to say, yes, I've received that, send me the next packet. And it does that over and over again until it's finished, and then you reset the CPU. So the HAL knows that the software is actually being loaded into RAM correctly. There's an acknowledgement protocol which goes back down the cable. So getting back to where I was at when I turned this on, I plugged it into HAL and booted HAL up. Partway through that process, HAL will then try to talk to the disk array. Now, the way it had been working before I had the Dylan was it would just get to the point where it would try and talk to the Dylan to load the software over the link, and it would just say there's no response, timing out, and it would just carry on booting, and then it would just sort of behave as a very big Quantel paint box. And all of the video features were just disabled because it knew it didn't have a disk array. So when I first powered this on, turned on HAL, booted up, I still got the same errors that I was getting when it wasn't even connected. So that was timeouts, can't find a Dylan, and it took a little bit of time to sort of go through, and I managed to find the serial connections, the 4 wires that run down the big data cable, and where they actually come out on here, just to verify that the signals were actually getting through. So what I wanted to see was some kind of packet coming in and arriving somewhere on this board, and then that would prove that the Dylan interface cards on HAL, the cables, the connections and driver chips on here were all working. And thankfully there was a very, very small little packet of data that would come in, and then HAL would just give up. That was probably because it was probably sending the first packet and it never got an ACK, an acknowledgement back, and it just gave up. That puzzled me, because it meant that it was actually arriving here, but the transputer wasn't responding with an acknowledgement. Now, I did a bit of probing around, did sort of basic sanity checks, and I found that the voltage on the 5-volt rail on the power supply was a little bit low. It was a bit low, so thankfully I managed to find the adjustment for that, readjusted it back up to, I think I set it to 5.1 volts, and that cured that problem. So it's a bit of a 2-stage boot process. The first part is loading the software over the link into RAM, resetting the CPU so then it can start processing the code that was delivered. The second stage is when the actual Quantel software starts to boot up and become alive, and what it will do is it will reset the hardware, configure things, and it would then either send a packet or something to HAL to say, hello, I'm here, and then I suspect what happens then is HAL will then say to Dylan, okay, please start spinning up your disks and become ready. And at that point, HAL then just waits, because it takes a minute or two for the Dylan to sequentially spin up all of these 20 hard disks that it's got inside it. That takes a little bit of time, so HAL just sort of sits there waiting, probably expecting some kind of acknowledgement back from the Dylan to say, I'm online, you can carry on. Now, it's that bit that doesn't seem to happen. The first stage works, it transfers the software and it starts booting. I'll go into that into a bit more detail in a minute, but then it just doesn't get any further. Now, what I can actually do is demonstrate this to you as live as things happen. So I've got a few things set up here. You can see on the screen we have the diagnostics output from HAL. HAL is currently booted up into like a semi-working state. It doesn't need to be fully booted because I only need access to the commands which talk to the Dylan. So you don't need to worry about those details. I just need to access a particular diagnostics menu. So Dylan is currently turned off. I've got a scope on in the just here, and that is connected up to one of the test points in Dylan, which is one of the specialized memory control pins on the transputer. These are sort of like multi-purpose pins depending on how you've got the memory configured. So it's this particular pin is really good just to see if there's activity on the CPU, to see what it's doing basically. You can also see things like the DRAM refresh, things like that. So it's a good general view on what the transputer, how active it is and what it's doing. So what I'm going to do first is show you what happens when you try and load the software to Dylan over HAL when there's no Dylan there, when it's switched off. Now the one we're particularly interested in is called Chat. Chat it's not talking about chatting to anything. It's basically Chatterdisk. So within Chat, we've got a number of options here. Now, the two that we're most interested in are boot and restart. Now, what boot does is transfer the software from HAL to the Dylan's transputer over that serial link. And literally that's all it does. It just loads the software and resets. The other command, restart, does exactly the same, but it then also tells Dylan to start operations. So when you do a boot command, it's literally just loading the software in and resetting it, and more than likely there's some routines that get run just to do some basic configuration of the hardware, and then it'll just sit there not really doing anything, and it's only when you do restart does it actually tell Dylan to, can you please come online and get things to a state where they can actually be used. So it's this two-stage boot process thing. So let's just do boot and you can see what happens. So we get these messages here: disk 1 boot failed, disk 1 comms and data links reset. So what that is actually trying to do is transfer the software from HAL to Dylan, and obviously it fails, and it looks like it actually tries twice. I would say, given that there's two copies of this error message here, it probably tries once, times out, tries again, times out, and then it gives up. So if I do restart, you'll see it does exactly the same thing. Right, let's turn on the Dylan. So Dylan is now powered on, but it has no software on it. So what you're seeing on the screen on the scope is the one of these test points, and what you're seeing there, I'm pretty certain, is the DRAM refresh that's happening. So it's just an ultra regular signal, and that happens. That's 5 microseconds, so 5, 10, about 15 microseconds apart. So that's not really doing much at all. So if I return back over to the console and I do boot, that will load the software from HAL into the transputer. So let's do that. Now it's going to happen very quickly. So if I press return, so you saw a load of activity right at the beginning, and it's now settled down to this other less regular activity. So yeah, you can see there's a whole load of stuff going on, and to me that looks very much like the CPU is running and things are happening. So in this state you'd expect things to be working, and it does indeed say disk boot successful on the console. Now if I try and do restart, which should start Dylan fully, you see that initial activity again where it's actually reloaded the software, and then it just settles back down into what it was doing before. But HAL is now waiting for Dylan to spin up the disks, for all the disks to come online, and then for it to confirm that everything's ready. So HAL is just waiting for Dylan now. But Dylan isn't doing anything, it's not spinning up the disks, and eventually, after a period of time, HAL will give up. There we go, it's just given up, and that was maybe a minute or two. So what I'm going to do now is actually speak a little bit about the process that I went from here on. I'm going to be talking a little bit more about the technical side of the hardware. I can speak about that because I now have a much better understanding on how Quantel did things. It's working on the previous machines has given me sort of a really great insight into, I kind of can preempt what Quantel would have done, and I think that does help. Another thing which is a massive help is I am actually now in contact with the guy who designed the HAL, and I'm in contact with the guy who designed the Dylan. So they have been able to offer some massive insights into how this machine actually works. It's fascinating talking to them. So I want to thank those guys for coming on board and actually trying to help get these machines back up and running. Stuff that they worked on, 20, 30, even 40 years ago. Right, so sit down, grab a cup of tea, it's going to get technical. Right, where do we start? Well, let's just have a look at a general overview on what is actually on the top here. So we've got 3 PCBs. We've got one here with a connector, another one here with a connector. These appear to be mirrors of each other, and yeah, there's probably no reason why these wouldn't be identical, because it's just more drives. This is the main sort of brains. We've got 3 big connectors on the back. One connects to the host, which is HAL. Actually, it didn't have to be HAL. It could have been one of the other machines like EditBox or Henry. Or Domino, that was another one that used the Dylan. And 2 other connectors which aren't used on HAL, because HAL can only operate one Dylan. But on the bigger systems like EditBox, Henry and Domino, you could actually have 3 or 4 of these Dylan disk arrays, and these are the connectors that would parallel through and connect to them. So as the connectors are here on the back, we can see banks of particular chips, and these are line drivers which drive the differential connections out to HAL. So those are all MECL, Motorola ECL signaling. So they run quite toasty. And then we've got a whole sea of 7.4 series chips. We've got logic, we've got a lot of IDT components, which are a lot of things like shift registers and things like that. And there is, of course, a number of program devices. These are all Altera CPLDs. They're CPLDs getting close to FPGAs. There's a few PAL devices as well, just doing some basic stuff. but you can see that if I cover up this here, that these parts here are all mirrors of each other. So really the brains of the Dylan is from here. You've got the transputer over in the corner, and it's this bit here which does most of the processing. So the actual drive connections themselves, as I mentioned in a previous video, these are SCSI discs. They are 50-pin, single-ended, the old school SCSI drives that we used to use on our Apple Macs and Atari STs and Commodore Amigas and all that sort of stuff. Now, as I also said in a previous video, there is 20 individual SCSI controllers on the Dylan because it operates all of the discs in parallel. And there is a lot of duplication of all the electronics which allow the brains of it here to talk to each of these SCSI controllers. Now, the particular controller that they're using is a QLogic FAS236. It's a SCSI processor, as they call it, and it's pretty much a one-stop solution for doing SCSI communications. It has its own built-in facilities for DMA. DMA is very, very important to this machine because the low interaction that the CPU has with each of the controllers. What this allows these controllers to do is to DMA the memory out of the buffer, which is these 4 little zip DRAM packages on each one. The data comes in, the video data comes in and is clocked into all of these DRAMs, and then the code that runs on the transputer then instructs all of these SCSI controllers to just transfer all of that data onto the disk, please. The transputer doesn't really have any interaction with the data that's actually flowing onto these disks. It's literally just overseeing the operation. One of the issues that you're going to have when you have a system like this is each of these SCSI controllers is its own unique thing. It has its own chip select line, it has its own interrupt line. It also has a pad bus, which is an 8-bit interface into the registers in the actual QLogic SCSI controller. And the CPU needs to be able to talk to each one of these individually. So that means each one of these, if you add them all up, 20 drives, that gives you 20 chip select lines that you have to deal with. A chip select line is literally a logic high or low. If it's low, it activates that chip. So because these are all bused together, the pad bus, which does all the register communication, is all bused together across all of these devices. You have to be able to select each chip individually to be able to talk to it. So you need a mechanism to allow the CPU to select which device it wants to talk to. And that's what these devices do here in the middle. There is a bus which is connected directly to the CPU, and it allows the CPU to talk to these 4 CPLDs, and what this gives it the ability to do is to switch to whichever SCSI controller that it actually wants to talk to. So this is where all the chip select lines are sent out to each of the devices, and the interrupt lines that come out of the SCSI controller, they come in, and then that generates an interrupt to the CPU. The interrupt line is used during DMA. So as I said, these run quite autonomously. The CPU doesn't really get involved too much. So it will just command one of these devices to transfer the data off the buffer to the disk. And once that's complete, the controller initiates an interrupt, which is basically saying, hey, I've finished doing my transfer. I thought I'd let you know in a way. So we also have those 20 interrupt lines coming in and getting consolidated together in these devices here, because there's no way you could feed 20 individual interrupt lines into the CPU. You just can't do that. So they're all consolidated together in these chips here. What about the actual video side? So that is entirely separate. There is a whole load. There's actually a 16-bit wide bus which comes from HAL. It's bidirectional, so there is also a line in this cable that actually says the data is flowing from Dylan to HAL, or whether it's flowing from HAL to Dylan. That data comes in parallel, and then using some of these other devices, what it does is it splits up the incoming video data and distributes it around the HAL. Now, I can actually go into a little bit more detail than that. The way that Quantel did this is they deliver the data in packets. Those packets are called thunks. So you have a thunk of data that would come in, and I believe it's about 400 kilobytes. So a big chunk of data will flow in, about 400 kilobytes, and then that will then be written to the disk in a single operation. So it can transfer that 400K really quite quickly over that 16-bit wide bus, which I think is running at 20 megahertz. So it's pretty quick. Now, what a lot of the electronics does is, as that parallel data is coming in, it splits it up. And this is all built, this is all just literally hardware run. It's not operated by the transputer at all. It's completely autonomous. So the parallel data flows in and it gets chopped up, and every 2 bytes ends up on a different drive. So the first bit of data will come in, 2 bytes will end up here, 2 bytes will end up here, 2 bytes will end up here, 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 here. And you go around continually like that. As the data is clocking in, that 400 kilobytes is coming in and flowing into these buffer RAMs, round and round and round until it's full and the thunk is complete. And that's when the transputer then instructs all of the disks, all of the disk controllers, to transfer the data out of the buffer onto the disks. Now, one extra thing that happens while it's doing this is there is some hardware on this which, as that data is coming in, it generates a parity of it, and that is sent to the 20th disk. So 19 disks contain the video data, and then the 20th disk contains a parity of the data which is written to all the other disks. This is for redundancy. So if one of these 20 drives suddenly dies, then you can detect it, you can remove the disk while it's all powered on, put the disk back in, bring the drive back up, and the Dylan will then read all of the data that's on these disks and rebuild that parity to write to the disk that had failed, so it can regenerate the lost data. So what else do we need to talk about? Well, the software that runs on this. So because we're able to talk to the engineers that designed this, I'm able to know that the software that is loaded on this is actually a multitasking operating system developed by Quantel themselves. Now it's multitasking because it has to do lots of things all at once. You might think it's simple, but it isn't. It's this bit here, it starts getting a bit complicated, because now I've spoken about generally how this works, how the thunks come in, get distributed around the disks, parity and all that sort of stuff. We need to get back to what happened when I was booting up this for the first time. this has been powered on. HAL has been powered on. It started to boot. Now what happens is the HAL will load the operating system for Dylan over the serial link. It will come into the RAM. I can actually see, and I've verified this is actually happening. And the Dylan will reset the CPU. The software starts to work, but then it doesn't start communicating back to HAL. Now, the first things that I started doing when this was happening was basic sanity checks. You know, are all the clocks running? Is there any bad connections? Is there anything visible wrong? And I went through and couldn't really find anything that was wrong. There were some capacitors which were a bit weak, and I've actually you probably can't see on camera, but I've actually replaced some of these with some through hole caps, a bit bodge style. So I started going around with my oscilloscope, probing points, looking at things, and there is various test points to look at things that the transputer might be doing. There is also error pins on the CPU that indicate that there's a software fault. The test points to allow you to see the activity between the transputer and its RAM showed a lot of activity. It certainly looked indicative of a multitasking operating system just doing its thing. Huge amount of activity. So it didn't look like it should be in the state that it was. It was just, I don't know, it's just stuck in obviously a weird state, and I don't really know what the problem is. So I started going a bit further back. So when this boots up, the software is loaded and the CPU is reset. And that allows me to then set up my oscilloscope so I can look for that reset signal, and then I can start looking at various signals around the board as the CPU literally just starts to execute. One of the first places I looked was at the chip select lines that connect to each of the SCSI controllers, because obviously this has been powered up. You don't know what state all the devices are in, the registers and all that sort of thing, so they need to be all reset and configured, ready for the system to start. And indeed what seems to happen is the software starts and it sequentially goes through each of the SCSI controllers, selecting each one, configuring the registers, then resetting the SCSI bus, and then moving on to the next drive. And it does this in a sequence. You can see here that I've got a number of green stickers. So you can see it over there in the far corner. We've got 3, 1, 2 and 0. Those numbers are actually the chip select line for that device. So that's chip select 0, chip select 1, 2, 3, and then it goes around the entire board. So I found that it was actually going through and sequentially selecting the SCSI controllers to configure them, which is totally and utterly expected, something that it should be doing. So from there, I went, okay, does it do them all? That was the first question that I asked. So I went around all the chip selects. It's actually quite easy to do on these QLogic SCSI controllers, because the chip select pin just so happens to be on one of the corners. So there you can see one of these QLogic devices, and this is chip select 0, and the chip select pin is actually just in this corner just here. So it was actually quite easy to probe each one and have a look on the scope. When I try to boot the HAL up, boot Dylan up, I could see those chip select lines activate, and then I'd known it configured that device. So I went through all of them And one thing I noticed was it got to number 12 and it stopped. So the chip select lines are all activated: 0, 1, 2, 3, 4, 5, the 4, 5, 6, 7, 8, 9, 10, 11, and then there was nothing on 12, and then nothing on 13, 14, 15, 16, 17. There's nothing on those ones either. So for some reason, the software is starting up and it's going around trying to configure all of these SCSI controllers. It's getting to number 12 and then it stops. Now, each one of these is configured about 5 or 6 milliseconds from each other, so it all happens really quite quickly. Within 100 milliseconds, the whole thing's over. So you have to restart the software again, and then it'll do the same thing. So this all happens very quickly, and it always does the same thing. It gets to number 12 and then stops. Now, looking at the rest of the circuits and all of the activity, that's all still happening. So I think it's like there's a task that's getting stuck for some reason, and I really can't identify why that is. The Quantel guys that I'm talking to, they've been a massive help, but we just haven't really managed to get to the bottom of it. It's a very difficult problem to resolve because the rest of it seems to be working fine. If there was a fault on the memory or some of this other logic, it would stop the entire transputer from running, but it doesn't seem to do that. It's literally just this one task. So I've been through and tried to figure out things that could cause that to happen, and everything I've checked seems to be fine. I'm a bit of a loss as to why this is doing what it's doing. So for example, the way the transputer talks to these CPLDs, which do all the chip selects, I've verified that that all works and it's all connected. There's no bad connections between anything. As I said, I've just been scratching my head, going through all these different things, trying to theorize what could stop it getting to number 12 and then stopping. So I think what is happening is something's stopping that task from getting to number 12 and it just stops, which means it probably doesn't get onto the next step of the process, and then that would be the point where the transputer would then open up dialog to HAL and everything would work normally. That just doesn't seem to happen. And yeah, that's pretty much where we are. Now the problem I've got from here is this has been sat on my desk now for quite a few months, and HAL a few months before that. So this has been blocking any kind of other video that I might be making for probably going on for 5 months. And I would like to move on to other projects, things like that. So unfortunately, what is going to happen is this is going to be fully reassembled and it's going to go back into storage. It's a great disappointment not to get this running. There we are. I've just rearranged the camera so I can actually talk to you in a bit more detail now. So yeah, we're at a bit of an impasse, unfortunately. I don't know how much more to proceed on this, and I said it's blocking other projects, so unfortunately it's going to have to go back out into storage. It's a big disappointment. I mean, not only have I ended up spending well, there was £100 on the Zulu SCSI controllers, which I was hoping to use in this. There has also been the time and effort that was taken to repair the power supplies. sourcing some of the replacement discs. I mean, that alone was getting on for like £100 or so. So I had really hoped to have this up and running by now, or at least to the point where I can actually talk to the Dylan and actually start looking at replacing these spinning discs with more modern solution. But yes, unfortunately we've not managed to get there. So I'm going to have to pack this away, put it into storage, and we're going to look at this another time. How long that's going to be, I have no idea. So I just want to thank everybody who has contributed to trying to get Dylan and the HAL up and running. Thank you very, very much for your support. There's no way I would have got this far without your help. So big thanks to all those people that have been involved. Of course, a big thanks to all my loyal patrons who continue to fund and help not always successfully restore these machines. So congratulations if you managed to get to the end of the video. Yeah, you managed to listen to me waffle on through all this stuff. So thank you very much. Give it a big like and thumbs up, comments, all that sort of stuff. That's always welcome down in the comment section. Thanks very much for watching, everybody, and I will be back soon to make these circuit boards up, because these are Quantel related, and it's for the emulator of the DPB 7001. So these are going to be helping us fix that. So a video on that will be coming up very, very soon indeed. Thanks very much, everybody, and I'll see you on the next video. Bye for now.